Picture this. You've got a single, perfectly designed Swiss Army knife for AI video generation. Instead of rummaging through a massive toolbox for a highly specific wrench every single time you want to edit a lighting layer or, say, extract a green screen matte, you just have one master key that literally does it all. Welcome to today's Explainer, where we're going to unpack a truly massive leap in graphics technology called UniVidX. This is a unified framework that is completely reimagining how we generate and manipulate the visual layers of video. Here is our roadmap for today. First, the video generation bottleneck. Second, enter the unified framework. Third, the 3 engine pillars. Fourth, real-world multimodal applications. And finally, big results with small data. Section 1, the video generation bottleneck. Okay, let's dive right into this by first looking at the glaring problem with the tools we're currently using. Pre-trained video diffusion models have become these incredibly powerful engines for simulating reality, right? But they have a major flaw. They're traditionally treated as one-trick ponies. The old way of doing things means training a completely separate network for every single specific task. Want to turn an RGB video into an alpha matte? Well, that's one model. Want to extract geometry? You're going to need another model. This completely locks the systems into fixed, rigid input-to-output mappings. And worse, working in isolation like this totally ignores how these visual layers naturally interact with each other in the real world. That leads to some super frustrating cross-modal inconsistencies when you actually try to stack the results together. So we clearly need a new way.
Section 2. Enter the unified framework.
And that brings us directly to the hero of our story, UniVidX. This framework was built from the ground up to break completely free from those rigid roles. But before we go any further, let's quickly define a crucial piece of academic jargon you're going to hear a lot in this explainer: modality. In the context of computer graphics, a modality is really just a distinct visual layer of a scene. You have your standard RGB, which is the normal color we all see, but beneath that you have albedo, which is the base texture without any lighting, alpha, which dictates transparency, and normal maps, which actually define the surface geometry and angles. And this brilliantly illustrates the concept. On one side, you see the standard RGB color layer of a village scene, but right next to it, you're looking at the normal map of that exact same scene, which details the precise underlying geometry. These layers are deeply, deeply correlated. They are intrinsically linked together to form the final image your eyes actually process.
So, what does this all mean? Well, it led the creators of UniVidX to pose one fundamental research question. Can we design a unified framework that allows any visual modality to act as a condition, meaning an input, or a target, meaning an output? Basically, can we make a system where you can arbitrarily swap these layers around? Solving this is incredibly complex, mostly because the model has to adapt to totally distinct modality distributions while simultaneously preserving its high-quality generative priors. That's essentially the model's fundamental understanding of reality that it was originally trained on.
Section 3, the 3 engine pillars. To actually solve this, the researchers had to completely redesign the engine. The UniVidX framework is built on 3 foundational pillars. Think of them as 3 distinct dynamic tools acting inside our Swiss Army knife. We're talking about SCM, DGL, and CMSA. Let's break down exactly what each one of these does under the hood. First up is Stochastic Condition Masking, or SCM for short. Remember how we said old models get stuck in one lane? Well, SCM totally prevents that by randomly partitioning the modalities during the training phase. It's kind of like a teacher giving a pop quiz. Sometimes they hand you the answer and ask you to find the equation, and other times they give you the equation and ask for the answer. By constantly randomizing what is an input and what is an output, the AI is literally forced to learn omni-directional generation. It learns the entire web of relationships, not just a single predictable path. Now, what's really interesting about this next piece is how it stops things from getting messy. The second pillar is Decoupled Gated LoRA, or DGL. LoRAs are essentially these small, highly adaptable modules attached to the main model. UniVidX assigns an independent LoRA to each specific modality. And crucially, these are gated. A modality-specific LoRA only activates when that exact modality is the target being generated. This is absolute genius because it completely stops the parameters from interfering with one another, preserving the vital native priors of the foundation model. The third pillar is Cross-Modal Self-Attention, or CMSA. You can think of this as the ultimate communication layer. When the model is generating multiple visual layers all at once, CMSA forces them to explicitly share keys and values, which is essentially the core context of the scene, while still allowing each individual layer to ask its own independent queries or questions.
This facilitates super dense information exchange. It ensures that your lighting layer perfectly aligns with your geometry layer. It guarantees spatio-temporal consistency across the entire board.
Section 4. Real-world multimodal applications. So what happens when you combine omnidirectional learning, isolated parameters, and tight cross-modal communication? You get this, an incredibly versatile matrix of real-world applications. Just look at the sheer variety of outputs here. Imagine being able to take a basic video of a man in a suit, and with just a text prompt like "sunshine at dusk," the model correctly alters the albedo, the irradiance, and the normal layers to completely relight the scene. Or imagine pulling a flawless, dynamic alpha matte of an animal without ever needing a green screen. It's wild. Just to prove this wasn't all purely academic theory, the researchers went ahead and built two specific models straight from this framework. First up is UniVid-Intrinsic, which handles RGB and intrinsic maps, unlocking capabilities like text-to-intrinsic generation, inverse rendering, and full-on video relighting. Second is UniVid-Alpha, which takes care of layers like transparency and background, mastering text to RGBA, highly advanced video matting, and seamless video inpainting. And here's the really crazy part. Between just these two models, this single unified framework collectively handles 15 distinct, highly complex graphics tasks. It supports 3 completely different paradigms: text to vision, vision to vision, and hybrid text and vision to vision. It's just an absolutely massive expansion of flexibility for creators. Section 5. Big results with small data. Let's move to something that genuinely blew my mind and see how this builds on the model's efficiency. You'd probably assume that teaching a model to master 15 different multimodal tasks would require, tens of millions of new video clips? In reality, it took fewer than 1,000 training videos per specific domain. I mean, in an industry where models routinely require millions upon millions of clips just to learn a single new trick, this is staggering. Because UniVidX is so expertly designed to leverage those existing video diffusion priors, those fundamental understandings of reality the base model already has, it requires remarkably little new data to learn these omnidirectional mappings. So the absolutely crucial point here is this. Despite being trained on tiny, hyper-specific datasets, the model doesn't just blindly memorize the data. It truly understands the underlying physics and the intricate layers of the visuals. This results in incredibly robust out-of-distribution generalization. Simply put, you can throw totally unpredictable in-the-wild videos at it, things it has literally never seen before, and it still performs exceptionally well. There's a quote from the paper that I think perfectly wraps up the core breakthrough we've been exploring today. They state that UniVidX enables versatile video generation by formulating diverse tasks as conditional generation problems within multimodal spaces. By stepping back and viewing these diverse tasks not as isolated problems but as interconnected pieces within a shared space, they've unlocked a completely new paradigm for video generation. It's flexible, it's consistent, and it's incredibly efficient. Which leaves us with this final massive question. If a single, incredibly data-efficient model can flawlessly relight scenes, pull mattes out of thin air, and generate complex physical geometry just by swapping its inputs and outputs, how is this going to completely reshape the future of everything from indie game development right up to major Hollywood visual effects? When the tools to manipulate the very fabric of digital reality become this unified and accessible, the creative possibilities are absolutely limitless. Thanks so much for joining me on this deep dive. I'll catch you in the next one.